So here we're practicing going from a state diagram all the way down to a circuit. This is just the circuit for the algorithmic state machine. We don't know what circuits are creating X1. We don't know what circuits are doing. We don't know what they're going to do when they receive a Z2. So we don't know the external world to this algorithmic state machine circuit. All we're doing is we're just designing it, and we're practicing. So let's call this 1. Let's call this path 2. Let's call this path 3. Let's call this path 6. Let's call this path 7. This path 8. And this path back 9. So we have paths 1, 2, 3. Paths 1 and 2 are associated with the state A. Paths 3, 4, and 5 are associated with state B. Paths 6 and 7 are associated with state C. Path 8, there's only one state, D, associated with it. And 9, there's just one state associated with it. All right, so that's our link paths or data paths. Okay, so I've drawn in the present states, and now what I want to do is document our inputs. So we have an input X1. We have, that's right here, we have an input, I think this is X1 and X2. We have an input here of X3. And there are no inputs in these two. Let's see, we have an input of X1 could be a 0 or a 1 here at state A. Let's assume this is an X1. So it could be a value of, for link path 3, it's a value of 0. For link path 4, X1's a value of 0. For link path 5, it's a value of a 1. So X2 has a value for link path 3. X2 has a value of 0. And for link path 4, it has a value of 1. For link path 5, it's not looked at. And X2 is not looked at up here. All right. Now in link path 6 and 7, we're looking at X3, which has a value of 0 and 1. We're not looking at X1 or X2. We're not looking at X3 up here. And then in states, algorithmic states D and E, we're not looking at any of them. Now, just because we're not looking at them, that means we got to block them out. We've got to tie X1 into this state. Okay, so now let's document the next states. Next states. So in link path 1, we go from state A, and then we go back to state A. For link path 2, we go down here to state B. For link path 3, we leave 3, and we go back up here to 1, or to A. D always goes to E, and E always goes back to A. Okay, so we finish this up with our outputs. And we have Z1, Z2, Z3, Z2, Z3, Z4, Z1, and Z3. All right, so we have Z1, 2, 3, and 4. Okay, in present state A, we have link path 1. Z1 is more, so it sets them both. In link path 2, it in addition sets Z2, which is Mealy. Remember, there's always zeros right here. Okay, state B, we set nothing. Nothing gets set here. There's nothing here. There's no Mealy or more here. So link path 3, everything is a 0. These guys are zeros. In link path 4, we set Z2. That's a Z2. Everything else is 0. In link path 5, we set Z3. In link path 6, well, Z3 and Z4 are both set Mealy style here in state C. So in both cases, 3 and 4 are set. These guys aren't looked at in either case. And then in state D, we're always setting Z1. And in state E, we're setting Z3. And that's it. So let's check our work. Yep, it's perfect. So we're going to scroll down here this next slide, and that's just a typed version of what we just did. So we've finished looking at the state diagram and drawing the state table. There's no way to collapse these states A and B. We can't combine A and B or B and C, and the outputs are all different. We're going to skip the implicant table. Now our goal is to build the transition table. So we're going to start off by trying to figure out how many flip-flops we need. We've got 1, 2, 3, 4, 5 states, so we need 3 flip-flops. Now we need to go from state A to state B. We need to go from B back to A, that's redundant. B to C, and B to D, C to D. So these are all the 1-bit changes we want. D to E, and E back to A. So A just has B and E next to it. We have 3 flip-flops, let's call them Q1, Q2, and Q3. So we want to put A 1-bit change away from B and 1-bit change away from E. So let's put A right here, B right here, and E right here. All right, now B's got to go to both C and D. So B's got to go to C, and B's got to go to D. D needs to go to E. C needs to go to D. Now how are we going to get C? This is a 2-bit change. How are we going to get C to go to D? I don't know. Let's go see how they did it. All right, let's see. A, B, C, E. C's got to go to D. Yeah. All right, so they're tolerating a 2-bit change right here. Right? They're tolerating this 2-bit change. So let's just go with the book's solution right here. Otherwise, if we went with mine, then we'd end up with a different circuit. So A is going to be a 0, 0, 0, B is going to be a 0, 0, 1, C is going to be a 0, 1, 1. So we just substitute all these numbers in here. So wherever we see an A, we replace it with a 0, 0, 0. Wherever we see a B, we replace it with 0, 0, 1. Wherever we see a C, we replace it with a 0, 1, 1. So that's our transition table. So there's our transition table. Next, our goal is to go from the transition table to the excitation table. We're going to do that by choosing JK flip-flops. So what I've got to be able to do is translate a Q, current Q, to a next Q. Let's see, that could be a remember, or it could be a reset. So in summary, that's the 0 dash. Now we could go from a 0, right here's a 0, go to a 1. So we need to be able to translate that into our stimulus of the JK flip-flop. So that could be a set or a toggle. So that's a 1 dash. And then we could go from a 1 to a 0. So that would be a reset or a toggle. So that would be a dash 1. Or we could go from a 1 to a 1. So that would be a set or a remember. So that's a dash 0. Now I'm ready to fill out this excitation table. I've drawn what I've copied from the top here down in blue. And now I'm going to write down what it takes to create these next Qs using J1, K1 to create that column, J2, K2 to create this column, and J3 and K3 to create that column. I start off by looking at this 0 going to this 0. And that's going to be a 0 dash, and I write it right here. This 0 goes to this 0, so that's another 0 dash. And this 0 goes to this 0. So that's another 0 dash. Okay, I've got a 0 going to a 0, that's another 0 dash. 0 going to a 0, another 0 dash. And a 0 going to a 1. 0 going to a 1 is a 1 dash. 0 going to a 0 is a 0 dash. 0 going to a 0 is a 0 dash. A 1 going to a 0 is a dash 1. 0 going to a 0 is a 0 dash. 0 going to a 1. The only mistake I made was going from here to here is a dash 0, so this should be a dash 0. Okay, so here is the new table. This is what I created in red right here. Now our goal is to build the circuit. So this is that table repeated, and what we want to do now is begin finding the equations for our outputs. This is going to be what we need to find equations for, all these things up here. These are going to be our inputs. 2, 4, 8, 16, 32, 64 rows in our truth table now. So let's just look at J and do a variable and a kernel map for these three. So we're going to start off here with J1, and this will be Q1, and this will be Q2, Q3. All right. What's J's value here when they're all zeros? Well, when both rows are 0, then we don't care about these inputs, and J1's going to be a 0. So I'll put a 0 right there. Now let's look at all three of these rows. Is J all the same? No. But it looks like it's whatever the value of x1 is. So 0, 0, 1 is going to be x1. Whatever x1's value is. Okay, now let's look at these two rows. Try to combine them. J1's value is x3. So 0, 1, 1 is x3. Finally, we have these last two rows. 0, 1, 0 doesn't matter what J is, and 1, 0, 0 doesn't matter what J1 is. So this is our truth table. All these here are don't cares. Our implicants look like this. So that gives us a J1 being Q2 bar Q3 x1, or Q2 Q3 x3. On to the next one. Okay, K1 is a 0 in 1, 0, 1. 1, 0, 1. K is a 0. And K is a 1 in 1, 0, 0. 1, 0, 0. So that's this, because the rest are don't cares. So let's see. Q1 doesn't matter. Q2 doesn't matter. K1 is going to equal Q3 bar. J2 is going to be 0 for all three of them 0. J2 is a 0, 1, 0. 0, 1, 0. We can't be sure what that is. These inputs that are don't cares are tricky, but that's the only way we're going to distinguish it. So let's see, 0, 1, 0. 0, 1, 0. It's only when x1 is a 0 and x2 is a 1. So we're going to put this pair in there, x1 bar x2. x1 bar x2. All right, don't care, and 0, 0. 1, 0, 1, 1, 0, 1 is a 0, and this is a 0. Okay, so our implicant is going to be this. So that's going to be x1 bar x2. All right, K2. A bunch of don't cares and a 0, 1 that directly matches x3. So K2 equals x3. J3, let's see, J3 matches up with what? X1. But then we've got a 1 down here we don't want. All right, we're going to have to draw a truth table for this. Well, we'd like these to be the same for this 0, 0, 0 state. Remember, we're trying to combine these. So we're going to write down x1 in the 0, 0 state. So we're going to write down x1 right here. And then we're going to write down a 0 down here at the 1, 0, 0. 1, 0, 0 is a 0. So J3, we can make this whole thing right here a big implicant. So J3 can equal Q1 bar X1. K3 is going to get complicated. We have 1, 0, 0. We're trying to collapse those into what? It's going to be a combination of x1 and x2. Can we write that down? Not x1, not x2. Right. Okay, so we can write this one down. 0, 0. That's easy. That's going to be easy. That's going to be easy. Okay, so we can do this in the same way we've done these others. So K3 right here is going to be not x1, not x2. Zeros are going to be for the 0, 1, 1. 0, 1, 1 state is going to be a 0. So those two zeros translate to 1, 0 there because we're combining these two rows. And then 1, 0, 1 is going to be a 1. 1, 0, 1 is going to be a 1. And I don't care about this one. So that's it. Okay, what can we do? We can make a big implicant right here. Let's call that one, it's going to equal, doesn't matter what Q1 is, Q2 is going to be a naught, Q2 naught, X1 bar, X2 bar. And then we can make another implicant right here to catch the remaining parts of 1, that 1 right there. So that's going to be Q1 by itself. Okay, so let's look at these outputs. Oh, we got a mixture of Mealy and more in here. So we're going to have to worry about that one. There's some Mealy in here. We're going to have to worry about that one. Yeah, worry about that one. This is the only pure more one, which is pretty easy. Z4 looks like it is Q2. Z4 equals Q2. Okay, so for the 0, 0, 0, Z1 is a 1. For the 0, 0, 1, Z1's a 0. For the 0, 1, 1, Z1's a 0. For the 1, 0, 1, Z1's a 1. 1, 0, 1, Z1's a 1. For the 1, 0, 0, Z1 is a 0. So the rest of these are don't cares. So Z1 is going to be, we can make a party out of this right here. So it's going to be Q1 bar And then Q2 is changing. Q3 is a 0. And this one's going to be or Q1, Q2 bar, Q3. Okay, so Z2 is going to be 0, 1, which is X1. 0, 1, 0. Oh, that's the same as J2. X1 bar, X2. 0 for 0, 1, 1. So my implicants are going to be right here. I can make one. So Z2 is going to equal, or this guy is all by itself, so it's going to be a long one. X1 bar X2. Okay, so Z3 is going to be 0, 0. 0, 0, 1, which parallels X1. All right. 1, 1. 0, 1, 1 is a 1. And then a 0 and a 1. So we can make a party of Q1 bar. Q2 is changing its mind. Q3. X1. And we can have another party right here of 4 to pick up this remaining 1. So this is Q1 doesn't matter. Q3 doesn't matter. Q2 is a 1. And then we got to pick up this guy. And we're done. These answers agree with the book. Boy, lots of work. What's the alternative? Start off with a truth table with 64 rows and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs. Try to do that right? Try to do this right? Yeah, it's a pain, but it's engineering and you get paid for it. So I would build the circuit by entering in all these equations into the simulator, building the combinatory circuits that develop all of our outputs and all of our JKs, adding the 3 flip-flops, and then tying them back, their outputs back into Q1, Q2, Q3 inputs. And then I'd be done. The other way is just to stop, don't write down these equations, and build a mux, a 3-input mux, Q1, Q2, Q3 input mux, and then write down the truth table as input to the mux. That's what we're going to do next.